I'm going to talk a little bit about a different point of view in the cloud and cloud security. And of course, NVIDIA is the visual computing company. So I'm going to talk about how you make secure your visual data. I'll talk about what that is as we go. But I thought before, just to get you interested, you don't have to listen to me say, how are people using visual computing and GPUs in the cloud? I thought I would quote a couple of legendary developers from the cloud space. So Jeff Dean, you may not know him from Google. He was originally one of the developers of Google Search, and he's now the vice president of deep learning at Google. He recently talked at our GPU developer conference earlier this year, and he said there were over 47 different applications running on the Google Cloud that use GPUs. One of the big clouds in Asia is, of course, Baidu. Andrew Ng was sort of the father of deep learning, deep learning at Stanford University, and he said at the same conference that within 5 years, 50% of their queries would be about speech or images. And when you do search on speech and images, that's not simply looking up something in a table. That's using deep learning in the background, in the cloud, to manage that. So let's step in a little bit and talk about what really is driving in the cloud the use of GPUs. So one is certainly high-performance computing. This was arguably one of the first cloud-like applications, even before people talked about cloud, because the numbers of computers that you need to solve these large, globally important problems, whether they're about global warming or climate change, predicting earthquakes, are solved using GPUs. The cloud, 5 of the world's largest cloud data centers already use GPUs today. And finally is virtualization, and specifically virtualization of the desktop. Lars from SAP talked about you don't need a traditional desktop today, and that's true to a certain extent, right? All of you probably run some sort of corporate application, SAP or otherwise, on your mobile device. But at the end of the day, there's a lot of things that you probably do at your organization that still need a desktop. Probably still need a Windows desktop. Right? Windows announced Windows 10, the ship date, is July 29th. They announced they'll start shipping. And I expect 10 years from now, people will still need to run Windows, some version of Windows, maybe not Windows 10. So how do you run Windows 10 securely in the cloud? So we'll talk a little bit about how you do that with GPUs. So how many people know what a GPU is, right? COMPUTEX, a lot of the talk about GPUs is about gaming, and yes, we do gaming, and we do gaming in the cloud, but basically a GPU is an accelerator. It's actually used in conjunction with a CPU. And CPUs are very good at doing several things at once. But when you deal with visual computing, many desktops that you want to run at the same time, deep learning, when you want to try to mimic the human brain with its millions and millions of connections, you need a processor or an accelerator that can do more things in parallel. So again, our GPUs typically work with a CPU from Intel or IBM or AMD, and we actually think that this trend is something that's going to continue. In fact, Intel just announced this week that they were spending $16 billion to buy an accelerator, floating point, or an FPGA accelerator, but still an accelerator that works with their CPU. So we think Intel's on the right track there with using a CPU with an accelerator. So let's talk a little bit about desktops and why would you secure a desktop in the cloud? So we have a great little SAP-related travel expense application, right? And I can run that on my phone. I just take a little picture of my expense, it uploads, and I can file my expense report on my phone. But when I want to go and look at when I want to go through and do something more complicated that's tied into a broader business process, I often still need to bring up my desktop. There's millions of lines of code, thousands of complicated applications that still run in a desktop and will, for the next 10 years, not likely to run as a small app in the cloud. So how do you give users, your enterprise users, mobility to not have to come into the office and run that application? How do you give IT simplicity? Right? Today, IT has to go and manage hundreds, thousands, tens of thousands of desktops, depending on the size of your organization. It's not just the great thing about the cloud is that the servers are all in the data center. You can go in one place and run it. How do you do that in the desktop? And finally, many of those desktop applications require more and more big data. If you're an oil company and you've got all the data from an oil well that you're drilling, right? You want to keep that secure in your data center. You maybe don't want to move it out to a desktop in a remote country. They may have some security concerns. And all sorts of data that you want to keep more secure in the data center. So I'll give you a little example on running this video. And the great thing is with applications like Google Maps, and the fact that every mobile processor, your laptop and your desktop, has some GPU in it. It may be built into the processor versus separate. So on your left, you get an experience very similar to what you would get on your cell phone. You can bring up Google Maps, pan, zoom, go in, and it's very smooth. Now the problem is, how many people have ever tried Google Maps in a VDI environment when it's running on a server in the desktop? It's actually not very usable, right? And the reason it's not very usable is because while even the very low-end processor in your cell phone or your laptop or your tablet has some sort of graphics acceleration in it, the processors in a server traditionally haven't. So there have been ways to go through and virtualize the desktop, of course, and they started with what was called CPU emulated. Instead of running the graphics in your device, you ran the graphics on the CPU in the server, and that was fairly slow. Then companies like Citrix and VMware figured out how to share a GPU. So they would put a GPU in the server and share it. But in order to do that, now I am the vice president of engineering, so I apologize. Some of my slides will get a little technical, though I won't show you any CUDA source code, so that's the good news. And anyhow, in a shared environment, the driver is actually sits in VMware, but is not the native driver that runs on your desktop. It's not the NVIDIA driver if you have an NVIDIA GPU. It's not the Intel driver if you have an Intel GPU. So the problem with shared graphics is that you don't get very good compatibility. A lot of the functions in your application may not display correctly. Now, we've had customers for years that have gone through and ran, if they could afford it, what's called pass-through. For every user that they wanted to support on the server, they put a dedicated GPU. The problem is that's very, very expensive, and it sort of defeats the use of having a shared server serving the graphics. And so about 1.5 years ago, NVIDIA developed a technology called vGPU, or virtual GPU. And what vGPU does is it does for the GPU what hypervisors like VMware and Zen do for server workloads. They virtualize the GPU and make it shared. So you're running the native NVIDIA graphics driver. So all your applications, whether it's an SAP application or your favorite computer game, run flawlessly and at full speed, but it's still shared, so it's affordable. So we'll go into a few slides and say, but is this secure, right? If I have multiple users sharing the GPU, How do I actually make that secure? So again, the basic idea is all of my data sits on the server. That server could be in my enterprise data center running over an enterprise network, or it could be in a cloud data center and running over the cloud. I actually flew here on one of my favorite airlines to fly when I'm flying to Taiwan, EVA Air, and I actually turned on the business channel. There was actually a 30-minute segment on how Amazon Web Services uses NVIDIA GPUs to do just this, to offer gaming and other types of shared graphic services from the Amazon cloud to any end user. So the next thing that you add, like I said, is inside the hypervisor, inside VMware or inside Citrix, you add a piece of code called the NVIDIA Grid vGPU Manager that controls how information flows through the hypervisor and is shared by users. The NVIDIA driver sits then in the guest OS. So if I have 5 or 10 users sharing a server, each one has their own NVIDIA device driver. The state of that device driver and the actual graphics commands are then passed to the device driver and onto the GPU. The data then flows back through the guest OS and out into the cloud. Now, again, you say that looks like the GPU is being shared, so how is security provided in that case? So again, there's several different things that are shared. You're sharing actually the frame buffer on the GPU that shares the user's image. In the case of vGPU, each user is given their own piece of the memory, their own frame buffer, so they're not actually shared. The channels are then how the commands flow back and forth. And we actually use the CPU memory management unit, the same mechanism in hardware, in your Intel or in your AMD CPU that the VMware hypervisor uses to make a server workload secure. We use that to make the graphics workload secure. Of course, there also then needs to be a memory management unit in the GPU to separate out the state. So again, this allows different virtual machines to be assigned to different users and share the GPU and securely send data back and forth from a single server with a single GPU to multiple end users in the cloud. So again, those are very sort of complicated few slides there. But again, that's how we provide security, and that's how we let you efficiently and cost-effectively go in and put a single GPU in a server and share that among multiple desktops. Now, the next thing, and again, Lars talked about all of the big data in the cloud. And big data can be numerical data, big tables and spreadsheets and my expense report, and that can actually be processed fairly well on a GPU. But again, when I start uploading images, when I start uploading video, when I start uploading voice data to the internet, how do I go through and process all of that? Google Maps today, right, is actually more accurate using deep learning to read the address on your house number or apartment number than actually having a person go in and read it. So that's actually done with a technology called deep learning. And deep learning, again, typically that runs in the cloud, is involved 2 different steps. The first thing you have to do, it may sound like magic, right? How does a computer understand what that house address is? How does it understand what a picture of a dog or a cat or a person is? Is you set up a neural network. That neural network has a series of stages in it. And each one of these stages runs on a different processor inside the GPU. Again, that's why with having hundreds or thousands of CUDA processing cores in the GPU, it can be done much more quickly than doing this on a CPU that may have only 10 or 12 or a few threads. So in the training, the first thing you need is you need to have a lot of sample images of what you want to recognize: a tree, a cat, a dog. And a data scientist sets up the neural network with the right types of parameters to differentiate these. Now, the secret is, again, this doesn't work well if you only have 5 or 10 pictures. In fact, deep neural networks as algorithms have been around since the 1980s. If anyone's out there online, you can Google deep neural networks in history, and you'll see the 1980s there were papers. I actually studied deep neural networks in college. I won't tell you when I was in college. And the problem was, I didn't have a lot of pictures of cats, right? If I was lucky, I might have gotten 10 or 20 pictures. You actually need to effectively train a deep neural network. You need not dozens or hundreds, but you need millions of pictures. So again, running through all the math behind a deep neural network with millions of pictures is very, very time-consuming to do, even if you have many GPUs. So again, the economies of putting GPUs in the cloud and using them for training, which is done one time and not continually, is very, very effective. So again, what I would do with my neural network, I would take my picture of my dog and I would run it through the network. And what happens is, it sets, using the parameters that are set, it'll come out and it'll make a guess, and it might say, that's a turtle. Now the data scientist, of course, looks at that and says, no, that's not a turtle. But if I go in and take one of those little dots there and I adjust the parameters there, I then go through and propagate backwards the pictures, determine what the best settings are to actually match the dog, and then I run through again. And I'll take another image and do that again and again. And I repeat that with, again, millions of images. And then what I get is a trained model. That trained model is a set of computer source code which actually models the network in the parameters, so that when I send something through that doesn't have to look exactly like the cat that I saw before, but I'll run through the network and it'll say a cat. And typically it'll give me some percentage of probability of how accurate the actual neural network thinks that it is. So again, the top part, the training, can take hundreds or thousands of GPUs and can take many hours to do, is you have millions of images going through. The model, once it's trained, can run on your cell phone, on the computer in your car, and very quickly, in fractions of a second, process an individual picture. And that's called the inference stage. So besides looking at YouTube videos and being able to identify cats and dogs, what other uses are there for training deep neural networks on images? Well, certainly is, for instance, making a vehicle classifier. If you want a self-driving car, one of the things that you certainly want to be able to do is pick out different objects in the road. A car, an SUV, a person, a tree, so that you don't run into them. This is actually a classifier that we wrote for one of our GPU computers that runs inside the car. In the scientific realm, we also use deep neural networks for problems that were traditionally run on large supercomputers. And again, this is a very interesting example that I found. It's run at Harvard University. And they have an electron microscope where they're actually taking images of the brain and trying to study how the brain works. So in effect, they're using a neural network to study the brain. So a little bit ironic but the current microscope actually generates 85 or 0.85 terabytes a day. And Harvard is using 250 NVIDIA GPUs to run that data through a neural network and process it. Later this year, Harvard will be upgrading their microscope. And they expect it'll be running about 50% of the time, 12 hours a day, and generating 1 gigabyte a second. So about 42 terabytes a day of data that they'll go through and process through that neural network. So again, a lot of interesting applications of neural networks. And in effect, so many different applications in the future will be using neural networks for the computer to, in effect, program the computer. And again, if you think back, whether it's analyzing neural net images of the brain, whether it's analyzing objects on the road or objects in a video, you could write a program to recognize one particular cat. But there aren't enough programmers in the world to write programs to recognize every single cat accurately in the world. And that's what the neural network does, is the computer program is in effect written by the computer. So again, a lot of data in the cloud, in being able to process that, make sense of that big data that's unstructured, right? An SAP HANA database is great for taking all your expenses and going through and doing analysis on your expenses. But without things like GPUs, very hard to process that unstructured data. There's a nice little video here, but I think in the interest of time, we won't go through actually run that. But again, this is an image of an individual synapse in the brain, and the different colors are the different colors of the proteins that make up that synapse. And what the neural network does is go through and identify all of those and color code those so that the scientists studying the brain can actually visualize what is going on at any particular time with the subject. Of course, today we can take neural networks and analyze a lot of data for Google or other social networking sites. We can take data from one car driving through the street and classify the images in it. But whether it's self-driving cars, it'll be millions, hundreds of millions of cars, or going from images to video, those demands will continue to increase. So one of the things that in NVIDIA research we're doing is working with the open source community and going through and taking the existing algorithms that run on a single GPU and looking at ways to make them run on multiple GPUs in parallel. And this isn't as easy as it sounds, but again, in this example, you do having 2 GPUs, and in the training phase, you go through and run the forward propagation, and then run the backward propagation, and then you need to synchronize the data and keep the 2 neural networks in step. After you synchronize the data, you then have to share the update. So this is what's called synchronous training. And again, why am I even presenting this? Is again, at NVIDIA, we're looking not only at how do we develop the GPU hardware, but how do we develop the software. So for instance, having very, very fast connections between 2 GPUs and a server is very, very important in this case for sharing the update. There's also asynchronous ways to do this where you skip the synchronization and only share the update is the final step. Finally, again, our vision of the future is very different from how, if you were an IT buyer and you came to COMPUTEX a few years ago, you might have gone to some of the hardware server vendors' booths, and they would have shown you, well, here's one size, here's a small server, and here's a medium server, here's a large server, and one has 2 memory DIMMs, and one has 4 memory DIMMs. And it's very different from how cloud providers, how an Amazon or Google builds their data center. They don't go to HP or Dell and say, tell me about the servers you have, and maybe I'll pick the one with the shiny color that I like or the others. They're going through and they're defining a data center. They're saying, I'm going to build a data center that's 100,000 square feet and has 1,000 racks of computers in it, and they may define 2 or 3 different types of racks. So we're working with all of those data center providers, and the companies that they buy from. Companies like Foxconn, companies like Quanta, companies like Tyan, and designing custom-built servers and custom-built racks of servers for running things like deep learning, things like visualization, where you have a standard GPU server, all the servers in the rack and maybe all the servers in tens or hundreds of racks are the same. And then you pick the NVIDIA software that you want based on the application. It could be for high-performance computing, it could be for deep learning, it could be for what we call our vGPU or grid. So thank you very much for coming, and it's a little bit of some of the things that we're doing in the cloud and securing the data in the cloud.